Good morning, students. Today we will start with the next section of unit number 5, which is cycloconverters. Basically, cycloconverters, as the name indicates here, in this cyclo means cycle, cycles means frequency. So this part indicates the frequency of some signal. Now which signal that we will see. Just please hold on. So sorry. Oh my God. So in this basically this cyclo word, it indicates the frequency of the input signal. Okay, and then converters is means the system which converts the frequency. So that means cycloconverter is such a power electronic application or circuit which converts the frequency of the input signal. Like till now, we have studied the power electronic circuitries wherein either AC is converted into DC, for example, phase controlled rectifier, or fixed DC is converted into variable DC, for example, choker, or fixed AC is converted into variable AC, that is AC voltage controller. Now here we are not converting the magnitude or amplitude of the voltage. We are not converting the amplitude of current. We are not converting the nature of the signal. In this particular power electronic circuit, which we call as cycloconverters, the frequency of the signal is converted. Okay, so these are also known as frequency converters, right? Okay, so you can check, make out from the name of the power electronic circuitry itself. So here cycle indicates frequency of the input signal. So our today's lecture is based on the basic concepts of cycloconverters, right? Okay, and then we will analyze the behavior of a cycle converter for a resistive load and for an inductive load also. Okay. Now let us come to the introduction of cycloconverters. So as I have stated earlier also, a device which converts input power at one frequency to output power at different frequency. So this indicates that this indicates that a cycloconverter is something which converts the power from one frequency level to another frequency level. Indirectly, the meaning of this statement is same, that a cycloconverter is a frequency converter, right? So at different frequency with one stage conversion is called as cycloconverter. One stage means in a single stage only this conversion takes place. It is not in a multiple steps. It is in single stage, single step, right? Okay. So a cycloconverter is thus a one stage frequency changer. So this is the another name of this particular circuit, right? So basically cycloconverters are of two types. That means either we can increase the frequency at the output, okay, or we can decrease the frequency at the output. That means we can increase the output frequency of the signal, or we can decrease the output frequency of the signal, right? Based on this, a cycloconverter is broadly categorized as step down converters, cycloconverters, and step up cycloconverters. So in step down cycloconverters, the output frequency F0 is lower than the input frequency Fs, or supply frequency. This is just a notation. You can use Fs, S for supply, F for frequency. You can use Fi also, I for input, F for frequency. Okay, so in step down transformer, generally the output frequency is less than the input frequency. But in step down cycloconverters, I mistakenly use the word transformer. In step down cycloconverters, the output frequency is less than input frequency. And in step up cycloconverters, the output frequency is greater than input frequency. Now, how do we achieve this phenomena? How a cycloconverter works? That is the next point that we will discuss. So all the things are mentioned here. Now history is also mentioned here. So you can go through this. As far as application is concerned, because it is a frequency changer, so generally we can use this power electronic circuitry for the speed control of AC drives. Now AC drives is nothing but, you can simply say, AC motor also. So drive becomes when when a control mechanism is used to control the speed of any motor. So that becomes drive. Okay, for example, a lift or excavators or elevators. All these are some common applications or examples of drive systems, right? Here AC drives means AC motor which is controlled, right? Okay, means whose speed is controlled, right? Okay. So because we are varying the frequency in cycloconverter, they are frequency variables, right? So you can use the frequency control technique for the speed control of AC motors by using cycloconverters, right? You can use them for induction heating by varying the frequency. Okay, because of that reason that the frequency is varied in cycloconverters, we can use this as induction heaters also, or in induction heating also. Static where is here is basically it can be used in the fax controller also, right? Fax devices, flexible AC transmission systems, right? For the reactive volt ampere generators, right? Okay, so all these applications are mentioned here for cycloconverters. The general use of cycloconverter is to provide either a variable frequency power from a fixed input frequency power. So that means it is converting a fixed frequency signal into variable frequency signal, right? Okay, so that can be used in AC motor speed control or fixed frequency power from a variable input frequency power. So that is also one of the applications, that it can convert a variable frequency input into the fixed frequency. Okay, so that means either it gives you a variable frequency signal or it gives you a fixed frequency signal from a variable frequency signal. That basically depends upon its application, where it is used. Okay, so let us come to the principle of cycloconverter operation. So basically cycloconverters, if we broadly understand uh, cycloconverters uh, have various categories, basically. Like step up, step down is one category, which is based on whether the output frequency is more than input frequency or output frequency is less than input frequency, right? Similarly, we have single phase cycloconverters, so we have three phase cycloconverters. Then we have single phase to single phase cycloconverters. Then we have single phase to three phase cycloconverters. Then we have three phase to single phase cycloconverters, or three phase to three phase cycloconverters, right? So it is all based on the various applications. We have all these categories, right? So just for the sake of understanding the principle of operation of cycloconverter, here we will try to understand the principle through a single phase to single phase cycloconverter, right? Okay, so and the basic principle of operation of step up as well as step down cycloconverter is presented here. The single phase to single phase cycloconverter, though seldom used in practice. So nowadays it is rarely used. Single phase to single phase cycloconverters are rarely used. We have more efficient cycloconverters nowadays, which we call as matrix converters, right? So matrix converters are generally used, which are high power, high high power devices, and they are more efficient as compared to conventional cycloconverters, right? So now, in a single phase to single phase. Now, single phase to single phase means that uh, at input as well as at output, you have the similar same phase, or you can say single phase only. Means the input supply that you give is single phase, and output is also single phase, right? Okay, because here we are talking about frequency conversion, right? So there are two types of circuitries. This is also one of the categories of cycloconverters. Either the circuit of cycloconverter can be a midpoint type, midpoint cycloconverter we call it, or the second category is the bridge type cycloconverter. This is basically based on their construction, how the SCRs are used in the circuit. Either the SCRs can be used as midpoint, okay, fine, like we have a center tap rectifier, okay, by using the center tap transformer you can convert design a center tap rectifier, okay. Similarly we have bridge rectifier also, because the SCRs are converted in bridge uh, shape, okay, formation, fine. Similarly here also we have the both categories, okay. But here we have we use generally multiple SCRs. Like in, if we talk about, let us say a bridge rectifier, or let us say we talk about AC voltage controller, which converts fixed AC into variable AC, right? There, let us say for single phase, if you have gone through the notes and all that, so you must have seen that in a single phase AC voltage controller, you use two SCRs which are connected in anti-parallel to one another, right? Anti-parallel to one another, right? This is how they are connected. Okay. And then you connect a load and then a supply. Okay. But out of these two SCRs, only one SCR will work at a time. For one half cycle, one SCR will work, and for the next half cycle, next SCR will work, whichever is forward biased, right? But here, in case of cycloconverters, uh, more number of SCRs are used simultaneously. Also, there are groups of SCRs basically. All the SCRs which are converted into cycloconverter, which are connected in the cycloconverter circuitry, they are divided into two groups, positive group and a negative group, right? So one or two SCRs from positive group or one or two SCRs from negative group are made to conduct. Okay, so here the type of commutation which is used for SCR can be both, means we can use forced commutation as well as natural commutation. So that all depends upon which SCR is made to conduct and which SCR is made to, which SCR is turned off basically, okay, purposefully. Okay, I hope you are very clear about the forced commutation and natural commutation. If not, I can repeat. Forced commutation is that technique to turn off an SCR in which the SCR is turned off forcefully by applying a reverse voltage across the SCR, conducting SCR, and by suppressing its current, means the current of conducting SCR, which we call as anode current, by suppressing the anode current to a value below holding current. So that is forced commutation, wherein forcefully the SCRs are turned off. In natural commutation, generally the SCRs are turned off naturally with the line voltage. That is why we also call such commutation as line commutation, right? Okay. Generally, the forced commutation is preferred in DC power electronic circuitries. For example, chopper, inverters, etc. And line commutation is preferred in phase control rectifier, AC voltage controllers, like that. But in cycloconverters, we can use both type of commutation, forced as well as natural, and that all depends upon which type of cycloconverters we are using for which type of application, right? So here you can see two cycloconverter circuitries are shown. If you can see it, this cycloconverter circuit is basically a single phase to single phase step up cycloconverter. Now, how can we say that this is a step up cycloconverter? Only when we will come to know that the output frequency is greater than input frequency. Okay, so that is the part of analysis. Okay, that we will cover later on. But this particular circuit which is shown here is is a midpoint type cycloconverter, because a center tap transformer is used here and the SCRs are used in pair, anti-parallel to one another in two groups. So you can see here, sorry, this P1 and P2. P here indicates positive and N indicates negative. So this P1 and P2 belong to positive group of SCRs, and N1 and N2 belong to negative group of SCRs. Now, why we are calling them positive group of SCRs and negative group of SCRs? That basically, is based on the fact that how the current and voltage, how the current flows through these SCRs and how the voltage will appear across these SCRs. Or you can say how the current will flow through load when these SCRs are conducting, and how the voltage will appear across load when these SCRs are conducting. Means when positive SCRs are conducting and when negative SCRs are conducting, right? So that also we will understand how they operate, right? Now here in this particular circuit, if you see, this is a bridge type cycloconverter. There are also two groups, positive group of SCRs and negative group of SCRs. In positive group of SCRs also you have 4 SCRs connected in bridge formation, and in negative group of SCRs also we have 4 SCRs connected in bridge formation, and a load is connected here. Supply is single phase, right, which is AC in nature, right? Now you will think that if input is AC, output is also a frequency based signal, then why forced commutation is used in these SCRs? So that we will understand why forced commutation is also used in cycloconverter circuits. Okay, so let us come to the midpoint cycloconverter first of all, and let us understand the working of a midpoint cycloconverter. As it is said that these are step up cycloconverters, so we will see that whether the output frequency is greater than input frequency or the output frequency is less than the input frequency. Okay, I hope this is very clear to you guys. Now you can see this is a midpoint type cycloconverter and its waveforms are shown here. Okay, so just analyze the functioning, and if you are well aware about the sorry, about the forward and reverse biased conduct mode of SCR. Okay, when an SCR is forward biased and when an SCR is reverse biased, if you are aware of this thing, so it is very easy to understand the working of this type of power electronic circuit. So for positive half cycle, so let us say for positive half cycle, A will be positive and B will be negative. Yes, for positive half cycle, A will be positive and B will be negative, where A and B are two ends of a center tapped transformer's secondary. Okay, here it is primary winding, it is secondary winding, right? So the center point is denoted with O, or basically 0. It is 0, okay, or O, whatever you want to understand. It is a notation given to the center tap, okay, or mid tap of the secondary winding of center tap transformer, right? So when A is positive and B is negative, so in this case, in this particular pair of SCRs, P1 and N1, among these two SCRs, P1 is forward biased, yes, and N1 is reverse biased because the cathode of N1 is connected to the positive cell supply and P1 is forward biased because the anode of P1 is connected to positive supply. Similarly, in this pair of SCR, P2 is reverse biased because the anode is under the effect of negative voltage, and in N2, which is forward biased because the cathode is under the effect of negative voltage. So cathode is connected to negative, so it is forward biased. Now, sorry. Now, so that means for positive half cycle P1 from this pair of SCR and N2 from this pair of SCR can conduct because they both are forward biased. Similarly, for negative half cycle, N1 is forward biased because for negative half cycle, A will be negative and B will be positive. So that means N1 will be forward biased and P2 is also forward biased. So that means for positive half cycle, you can write down somewhere if you want. For positive half cycle, P1 and N2 will conduct, means they are forward biased, and for negative half cycle, N1 and P2 will conduct because for negative half cycle, these two are forward biased, right? Now, we do not make both the SCRs which are forward biased for a particular half cycle to conduct simultaneously. Okay, so for positive half cycle, first of all, P1 is triggered. Now, how do we trigger the SCR? By providing a sufficient relevant gate pulse at the gate terminal of an SCR. Okay, so first of all, let us say P1 is triggered. So P1 is triggered. You can say as soon as P1 is triggered, you'll get some output. You'll get some output as shown here. You'll get some output, right? So let us say at some omega T1, P1 is turned off. Now P1 here is turned off by using forced commutation method. Why? Because P1 is conducting SCR. Still at omega T1 you can see you have a positive half cycle. So that means at omega T1 also your P1 will remain forward biased. It will not be reverse biased here. So that means you cannot turn off P1 naturally. You need to apply a forced reverse voltage across it to turn it off. So forced commutation is used. So at omega T1, P1 is turned off. So the next SCR of this pair means P1 and N2. From P1 and N2. Now N2 is triggered at omega T1 by providing a sufficient pulse at the gate of this SCR. Now, then N2 is made to conduct for certain duration. Then at omega T2, N2 is force commutated and P1 is turned off because P1 still is forward biased. You can see, if you are well aware to understand the waveforms, you can see very clearly that this is the positive envelope of the input supply and this is the negative envelope of input supply, right? So you can see that here P1 is still forward biased, so it is easy to conduct this SCR. It is easy to trigger this SCR. So at omega T2, P1 is again triggered. It's made to conduct for certain duration. Then at omega T3, it is turned off forcefully again. Forced commutation method apply किया गया. तो omega T3 पे इसको forced commutate किया गया P1 को और N2 को फिर से ट्रिगर किया गया और इसी तरह से पॉजिटिव हाफ साइकिल के लिए आप देख सकते हो आपको कुछ आउटपुट मिला. ठीक है. अब you must have noticed one thing, that when P1 is conducting, it is following the positive envelope of the supply. When N2 is conducting, it is following the negative envelope of the supply. Why it is happening? Now let us see this using the sign convention. Okay, now the positive direction of output current and output voltage is shown here. Okay, so until unless it is specified, we will assume these directions of current and voltage as positive. आउटपुट करंट एंड आउटपुट वोल्टेज एज पॉजिटिव, हम इन्हीं को पॉजिटिव मानेंगे. ठीक है. अब लेट अस सी, आपने P1 को पहले ट्रिगर किया, पॉजिटिव हाफ साइकिल थी, A पॉजिटिव है, B नेगेटिव है पॉजिटिव हाफ साइकिल के लिए. P1 फॉरवर्ड बायस है इस पेयर से, N2 फॉरवर्ड बायस है लोअर पेयर से, राइट. ओके, सो sorry. Now, so let us say P1 is triggered at omega t is equal to 0. Okay, so the current will flow in this way. This is how current will flow. आपने बेशक N2 forward bias है, but you have not triggered this SCR. So this is because the feature of an SCR that until unless you trigger it, it will not conduct. Though it is forward biased, it will not conduct. So it will behave as an open path, right? So for positive half cycle, when P1 is triggered at omega t is equal to 0, the current will flow in this manner. So that means the current which is flowing through P1 is in the direction of output current, reference current. तो जो reference direction है उसी के साथ है. So that means the current that flows through load when P1 is conducting for positive half cycle, the direction of load current will remain positive. I repeat, when P1 is conducting for positive half cycle, the direction of current through load is positive, right? Okay, and hence the direction of voltage will also be positive, and that is why the output voltage and output current in this case are positive. So it is following the positive envelope of the supply. Now, how come we have this negative envelope? Basically, A is positive and B is negative, right? So this voltage is, what is this voltage? This voltage is VAB, means B to A, right? Means B to A. Okay, so that means अब इसमें क्या है, इसमें N2 कंडक्ट कर रहा है. And why N2 is conducting? N2 is conducting because of this negative terminal, क्योंकि आपका जो सर्किट का लोअर एंड है वो नेगेटिव है. बिकॉज ऑफ दैट इट इज conducting, right? Now that means for N2 VAB is equal to minus VBA. I hope you are well aware about these sign conventions, right? So that means जो P1 के लिए VAB है वो N2 के लिए minus VBA है. Now what is the nature of VAB? It is sinusoidal, so it is positive half cycle. तो उसका उल्टा क्या होगा? Negative half cycle. तो ये negative envelope है basically. The voltage is same. Okay. Now let us see that at omega T1, P1 is turned off by forced commutation, right? Now N2 is triggered. Okay, now what will be the direction of current? अब इस SCR से current cannot flow in this direction. I hope you know this thing. Why? Because current cannot flow from cathode to anode, right? It will flow from anode to cathode only. तो एनोड करंट होता है, जो SCR करंट होता है वो तो एनोड से कैथोड ही फ्लो करता है SCR में, राइट? सो व्हाट विल बी द डायरेक्शन ऑफ करंट? द डायरेक्शन ऑफ करंट विल बी like this. Now you can see that the current that is flowing through load, the current that is flowing through load when N2 is conducting is opposite to the reference direction of load current. Reference direction of load current. And that is why the current direction in this case, when N2 is conducting, is opposite, means negative. And when the direction of current is negative, the output voltage will also reverse its direction. It will become positive and minus. So that is why it is following the negative envelope of the supply. So that means, and this is the reason that we have categorized these SCRs in positive group and negative group. You can see from this waveform, in this waveform, complete waveform, all the positive P1, 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 P2, P2, they are following the positive envelope of the supply, and all the N2, N2, N1, they are following the negative envelope of the supply, and that is why we call them positive group of SCRs and negative group of SCRs, because due to positive group of SCRs, the current that flows through load and the voltage that appears across load, means I node and V node, they are positive, okay, according to the reference direction, right? Similarly, the direction of output current and output voltage across load when the negative group of SCRs or any of the negative group of SCRs conduct, right? So the direction is negative, okay. So from this particular circuit diagram, I hope this thing is very clear to you guys, that why we are calling them positive and negative group and how a cycloconverter works, okay. So both commutations are used here. So let us say once at omega t is equal to pi here, this point is omega t is equal to pi, okay, it is equal to pi, right? So at this particular point, you can see the negative half cycle will start. Actually, this is the positive half cycle, and this is the negative. Actual cycle तो यही है, ये तो इसका रिफ्लेक्शन दिखा रखा है, जो मैंने अभी थोड़ी देर पहले बताया कि VAB is equal to minus VBA, right? ओके, तो अभी नेगेटिव हाफ साइकिल शुरू हुआ, तो जैसे ही नेगेटिव हाफ साइकिल शुरू होगा, क्या होगा, P1 जो कि फॉरवर्ड बायस था और N2 जो कि फॉरवर्ड बायस था, वो नेचुरली कॉम्यूटेट हो जाएंगे. Now you can see here the natural commutation has come into scenario. So that means forced commutation is used, and as well as natural commutation is also used, right? Now what will happen for negative half cycle? For negative half cycle, you can see N1 and P2. These two SCRs will become forward biased. Now for negative half cycle, A is negative, yes, and B is positive. So for P2 it is voltage from VBA. It is VBA. It is VBA, right? Voltage from A to P. And for N1, it is minus VAB. It is minus VAB, right? Okay. So that is why this negative envelope and positive envelope has appeared here, right? Okay. So it is clearly mentioned. देखो लिखा हुआ है supply voltage envelope, right? Okay. So ये envelope है basically, और ये इस वजह से VBA और VAB वाला concept जो हम use करते हैं generally electrical systems में, network analysis के अंदर, अगर आपको याद है, ठीक है. तो इसमें क्या होगा, मान लीजिए ओमेगा टी इज इक्वल टू पाई पे आपने क्या किया, P2 को ट्रिगर किया. अब देखो P2 को ट्रिगर करते हैं तो करंट की डायरेक्शन क्या होगी, करंट ऐसे फ्लो करेगा, करंट एनोड से कैथोड की तरफ जा रहा है, ये तो ऑन है, ठीक है. तो अब डायरेक्शन अगर आप मेजर करो तो बोथ डायरेक्शंस आर सेम, तो करंट इज पॉजिटिव and voltage will also be positive, and that is why the voltage, output voltage and output current because of P2 will be positive, right? Okay. Similarly, okay, let us say at some omega t, let us say some omega t value here, okay, any value. Okay, so that means we have made to conduct P2 from omega t pi to some duration, right? Okay, so at some omega t after pi we have forced commutated P2, उसको हमने फोर्स कम्यूटेट कर दिया। तो जब हमने उसे फोर्स कम्यूटेट किया तो हमने देखा N1 भी तो फॉरवर्ड बायस है, तो हमने N1 को ट्रिगर किया। तो जब हमने N1 को ट्रिगर किया तो N1 को ट्रिगर करके क्या हुआ, अब देखते हैं करंट कैसे फ्लो करेगा। देखो करंट हमें ऐसे तो नहीं जा सकता इसमें, ये तो कैथोड से एनोड हो गया है ना, तो करंट कैसे जाएगा, एनोड टू कैथोड, एंड लेट अस सी द डायरेक्शन ऑफ करंट। करंट विल फ्लो इन दिस now current will flow in this manner. Okay, so you can see that the direction of load current and load voltage because of the conduction of N1 is reversed, and that is why you will get a negative envelope of the output voltage. अब यहां तक तो आपको ये चीज क्लियर हो गई होगी। अब why we are calling it as step up transformer, why we are calling it as step up transformer? Now let us see, this is one cycle, yes, दिस इज वन साइकिल। एक साइकिल क्या होता है, ये साइकिल ही तो है, एक साइकिल, दो साइकिल और तीन साइकिल। यहां तक आ गया आपके पास, आपकी सप्लाई वोल्टेज का हाफ ही साइकिल आया और आउटपुट में आपके पास कितने आ गए, तीन साइकिल। लेटर से 4 साइकिल, 5 साइकिल, 6 साइकिल। जैसे ही आपका पूरा एक साइकिल कंप्लीट हुआ आपका आउटपुट वोल्टेज क्या मिला, 6 साइकिल। तो एफ नोट कितना हुआ, 6 हर्ट्ज। लेटर से F1 कितना था, 1 हर्ट्ज, FS सॉरी 1 हर्ट्ज। तो आपको आउटपुट वोल्टेज फ्रीक्वेंसी जो मिली वो इनपुट से ज्यादा मिली, एंड दैट इज व्हाई इट इज स्टेप अप ट्रांसफॉर्मर। सो गाइस, दिस इज इट फॉर टुडेस लेक्चर। इफ यू हैव एनी क्वेश्चन यू आर मोस्ट वेलकम विथ योर क्वेरी। So similarly, bridge type cycloconverter also the same type of working, it has same type of, the only difference is that here the SCRs they work in pair basically. So if you have a hand carry you can ask me. Chalo, thank you so much guys.